So let's look at another one here where we're going to do graphing. It's going to be kind of similar to the last one with a slight twist to what we had did before. But let's go through the kind of the steps so far that we've been taking. First off, looking at the domain. Now if we look at the domain, we're really again talking about the denominator set equal to 0. But if you're looking at this and you're trying to think about solving for x and you subtract the 1 over, and you'll see that, well, take square root, we're back in imaginary numbers yet again. Now technically what that tells us is for all real numbers, the denominator is never equal to 0 without involving some kind of imaginary numbers. So for us, we're actually not going to have anything for the domain in particular to look at. It's actually still going to be all real numbers. So just because we have a denominator doesn't necessarily mean that the domain will be limited by some numbers. In this case, this is a denominator that's never equal to 0, and so the domain is all real numbers. This also informs us about the asymptotes. So for the asymptotes, for vertical asymptotes, we're not going to have any vertical asymptotes. And that's because the denominator is not equal to 0 for real numbers at least. So there's no vertical asymptotes. So let's talk about the horizontal asymptotes. Well, I'm just going to kind of use the shortcut way of getting there without having to go into too much thought about limits and things like that. For this kind of function, notice how there's an x cubed on top, but not an x cubed on the denominator. So what we did in college algebra was to put an x cubed number in the denominator, x cubed term I should say, and look at the leading coefficients. Well, now you're seeing a 1 divided by a 0, which doesn't exist. That doesn't work. So for us, there are actually in this case no horizontal asymptotes either. So we don't have any vertical, we don't have any horizontal. The last other kind of vertical asymptote out there is the slant asymptote. And if you recall, slant asymptotes only happen when the degree of the numerator is exactly 1 more than the degree of the denominator. And by that I mean the highest power of x in the denominator is 2. For the numerator it's 3. So this is a candidate for having a slant asymptote. To figure out what the slant asymptote is, we divide the numerator by the denominator. In this case, we're going to have to use long polynomial division in order to facilitate this. So what we're going to do here is take x squared plus 1, divide it into x cubed. But that's not all we have to do here. Since our dividend, what we're dividing into, doesn't have an x squared term, we'll put a 0x squared, a 0x, and a 0 to fill out all the other powers of x in descending order. And then we'll follow the process of long polynomial division here. The first thing to do is to multiply by x. And that x will multiply to both the x squared and to the 1 to give us x cubed plus x. Now, as we did before, this is subtracting, so these will turn into negatives. And we'll have basically a 0x squared minus x. But we don't even need to include the 0x squared here. It's just really going to be just negative x. And so even if we brought down the next thing, which is a 0, we can't divide any further because our divisor has an x squared and what we're trying to divide into has a lower degree. So this is actually all the division that happens here. We just have an x. That's what we call the quotient. And this down here is what we call the remainder. So for the slant asymptote, y equals the quotient is the equation of the slant asymptote. So here the slant asymptote is y equals x. So now we figured out all our asymptote business that we have to do. We'll go through now and figure out the intercepts. So starting off with the x-intercept, we set it equal to 0, solve for x. Well, here's another situation where we're really just looking at the numerator equal to 0, which tells us that x is equal to 0. And we expect to see the same for the y-intercept if we try to determine that by plugging in 0 for x. 0 cubed divided by 0 squared plus 1, 0 divided by 1 or 0. So the origin is both x and y-intercept here. Now comes the fun part, trying to figure out the increasing, decreasing intervals, local max and local min. So to find the increasing and decreasing intervals, we have to start with the first derivative. So let me write down the original function real quick. Well, it's right up here above. So we're going to use that to find the first derivative. Again, another case where we have to use the quotient rule. So here we go. Low d high minus high d low, all over the square of what's below. Okay, once we simplify this down, looks like we're going to get something like 3x to the fourth plus 3x squared minus 2x to the fourth up on top. So that should reduce down to be x to the fourth plus 3x squared on top. That's our first derivative. Now, as before, we'll consider where the second derivative is equal, first derivative is equal to 0, and also where the first derivative does not exist. Well, to solve where it's equal to 0, like before, we just have to set the first derivative equal to 0. And the numerator is all that's going to influence this. The denominator basically will cancel out. So we have to take x to the fourth plus 3x squared equal to 0 to solve. So if we try to solve this, we have x squared times x squared plus 3 equal to 0. And if we try setting these both equal to 0 here, we'll have x equal to 0 and x squared equal to negative 3, which we see automatically at that point. This one's going into imaginary, so we're just going to ignore that and just use that as our only number. Now, on the other hand, where we talk about does not exist, denominator equal to 0. But it's just the same basic denominator we started out with, just raised to the second power, which still doesn't remove the fact that we're still just dealing with x squared plus 1. And that's imaginary solutions, so no real solution. So no need to worry about the denominator again being to 0 and the first derivative not existing. So we only have one critical value to work with, and that's just x equal to 0. So if we try to check out what's going on there, we'll plug in a negative 1 and a 1 into our derivative, first derivative here. So I'll just kind of write it out here. If we plug in f prime of negative 1, negative 1 to the fourth plus 3 times negative 1 squared over negative 1 squared, plus 1 all squared. Well, notice we'll have something like 4 divided by 4, which is just equal to 1. So we see it's positive. That tells us it's increasing. If we plug in 1, and basically the same exact numbers will show up in the calculation. We'll still have positive 4 divided by positive 4, positive 1. It's still increasing. So what that tells us is this thing is always increasing. It never actually turns around and decreases at any point in its graph. And now the only other thing we might look at then is its second derivative, and so to check the concavity. Now again, that's kind of the awkward thing to do because we have to think about second derivative in this case. But let me just go ahead and write out the second derivative rather than going through all the steps for it. It pretty much mirrors what we did in the example before this one. So going through all the steps in the first derivative, second derivative here, this is what you would get. Negative 2x to the third plus 6x all over x squared plus 1 raised to the third power. Now we're going to have to look at where is the second derivative equal to 0. This was f of x, by the way. Sorry about that. So where is f double prime of x equal to 0? We're not going to worry about does not exist like we did the first derivative. Denominator didn't change in any significant way, so we don't have to worry about the denominator. It's still the same. We do have to think about where is the second derivative equal to 0 though, and see if that didn't turn into something different. Okay, so if I set this equal to 0, it again just works out to be the numerator. Set that equal to 0, solve for x. If we factor out, I'm going to factor out negative 2x. We have negative 2x and then x squared minus 3 equal to 0. So we have two factors, negative 2x equal to 0, x squared minus 3 equal to 0. So what we'll get is we'll get an x equal to 0, and over here when we add the 3, we can actually then think about the square root, because it's now a positive 3. So we're actually going to get negative square root 3 and positive square root 3. So we have three different numbers now to look at for the second derivative. Critical values of sorts, like we had for the first derivative. So let's look at this on the number line. Kind of awkward numbers, the square root 3, but we're not really plugging in those numbers. We just have to look at numbers close by. So close by numbers to check: negative 2, negative 1, 1, and 2. So we'll set up these intervals here. These are the intervals where we're going to check again for concave up or concave down. 4 intervals to look at. Okay. We'll be plugging in for the second derivative. So y double prime is that kind of large derivative thing from up above. So we're plugging in here, and it's just to see what we get, positive or negative. Thankfully the numbers we're plugging in are not super serious numbers, they're fairly straightforward numbers. We plug in the negative 2. It's actually going to be a fairly big calculation, but again, just let a calculator help out with this. But we should get a positive number out, which tells us concave up. If we plug in a negative 1, it's actually going to turn to a negative, be concave down. If we plug in a positive 1, it's actually going to turn back to positive, be concave up. And if you plug in a 2, it's actually going to turn back to negative and go concave down. Alrighty, so that's going to be what's going to happen here. Plugging in the negative 2, negative 1, 1, and 2, positive, negative, positive, negative. That also tells us that all three of these locations are all inflection points. So now we know all this information about the function. We know it's concave up on the interval from negative infinity to negative square root 3 and also 0 to square root 3. It's going to be concave down on the interval from negative square root 3 to 0 and also square root 3 to infinity. Alright, so that's a lot to take in, but that's going to be where it's concave up and concave down. The inflection points, so we had three of them: x equals negative square root 3, x equals 0, and x equals square root 3. Just to show you the process behind calculating the y, I'll plug it in here. We're going back again to the very original function. We have to plug this in for x, which in the original f of x equals would look something like this. Now, this is a real kind of awkward number. It's approximately equal to a negative 1.3, and that's really all we need to know. If we plug in for 0, we'll also get out 0. If we plug in for square root 3, we're basically going to get approximately positive 1.3. So those are going to tell us the xy coordinates for each of the inflection points. And now we're ready to put this together into the graph. So let me kind of lay this out here, kind of show you all what's going on. Now, we didn't have much in the way of intercepts, asymptotes, really anything much at all. We do have the 0, 0 as the location of the both x and y intercept. And then we had the vertical, we had no vertical, no horizontal, but we had a slant asymptote of y equals x. And y equals x is just this diagonal line going straight through the origin. So that's what we're looking at here for the slant asymptote. It may be different kinds of lines depending upon what we got for the slant asymptote. We did not have any local max or min because the function was always increasing, but we did have some interesting things to say about the concavity, obviously from up above. We had an inflection point. Kind of spread this out here so we can write down those inflection points at negative square root 3 and negative 1.3. Now that's kind of in an awkward place, but it's kind of over here somewhere. And then 0, 0 was an inflection point, and then square root 3 and 1.3, which would be somewhere in this vicinity here. So how this is going to work is it's got to be concave up to begin with, so it kind of comes in like this, and then it goes concave down, and then it goes concave up. It's a really kind of weird looking graph, but this is the best I can do to make it look good. So it's concave up in here, concave down in here, concave up, and then it ends off the whole thing by going concave down. Notice how I had to cross through the slant asymptote a few times. I was kind of forced to do that in order to make the shape the right way. And it's okay to cross a slant asymptote. It's just the vertical asymptotes that we never cross.